Hi there! Now we will discuss machine learning quality metrics. We will cover classification, regression, and ranking problem statement. Let us start from the observing of machine learning model quality in production. Basically, if you deploy your machine learning model to production, you might see the picture like this. So that's the quality degradation in time. Basically, this happens just because things change. Imagine yourself solving fraud detection problem, for example for banking transactions. While you create your system and use it in production, bad actors also learn and try to fool your system. This is why it's important to measure quality of your model in time and see whether it started to decrease. If the quality started to decrease, then probably you need to update your model in order to learn new patterns and make sure you made your model again relevant. So that's why it's very important to not only measure model performance once after you complete all the experiments and train the final model, but also continue to measure in the same metrics over time during production. So yes, you can track the same metrics during model development, and for example, if for classification you used metrics like precision and recall, you can keep tracking them in production. For regression, you can continue to use metrics like mean absolute percentage error or root mean squared error. For ranking, you can go to DCG, NDCG, or top K accuracy score. So whatever you used for experiments works for monitoring. One more thing I want to warn you about is labeling data, because, well, in order to calculate almost all classification, regression, and ranking quality metrics, we need to have not only model's output, but the right labels as well. So if you do not get those labels automatically, consider a manual process of data labeling, at least for a part of your data. Now let's see an example of quality dashboard, and for showing an example, I'm going to switch to the browser and I go to demo.evidentlyai.com. Here you can see the example of the dashboard Evidently can give to you. So I would go for demo project for bikes. This is the very well-known problem statement when we need to predict how many bikes will be taken to rent depending on the weather and season conditions. So let us move to the quality metrics. For example, here, as we solve regression problem, we can use mean absolute error and mean absolute percentage error, and basically this is how you can track those metrics in time. We have the time values and the metric score, so that you can zoom in and see what's going on with the metric. Let's go back to our slides. Now let's discuss classification quality metrics. Basically, in order to calculate any classification quality metrics, we need to first generate models predictions, and for doing that we need to feed our input data, input features to the model, and then we will be able to generate either predicted labels or predicted probabilities. And this data we need to compare with the actual labels. Here is the list of the most popular classification metrics. Those are accuracy, precision and recall, F-measure, receiver operation curve, the area under the curve, and logarithmic class. Now let's discuss these metrics. Basically, accuracy score is the most popular metric, I would say, for a classification problem because it's very well interpretable. Basically, it gives us the share of correct predictions. The only thing I want to warn you about is unbalanced classification, because if your dataset is very unbalanced, again, like in the fraud detection problem which we just discussed, this metric can easily fool you. For example, if your model always assess the majority class to all the objects, in our case non-fraud, then the accuracy score will be high just because the share of such labels is high in your dataset. So be very careful with unbalanced class. Precision and recall is a couple of metrics which works quite well with unbalanced problem statement. Precision helps us to measure the correctness when a model predicts the target class, and recall shows us the ability to find all the objects which belongs to the target class. So basically, those metrics are better to use all together. Sometimes it's quite hard to decide what is the most important to you, like precision or recall, or maybe both are important. And in this case, you can go for F1 score, because this is the harmonic mean of precision and recall. Harmonic mean is very convenient to us because it's always closer to the smallest metric. If precision is smaller, then your F measure will be closer to precision, and if recall is smaller, it will be closer to recall. So you will never miss the issue with any of those metrics. The next couple of metrics are specifically good for probabilistic problem statement. Area under the receiver operating curve helps us to measure quality of the ranking for our model. I mean, if we assume that ideally we would rank our objects the following: first all the objects from target class and then all the objects from non-target class, and we order them by the predicted probabilities, then the higher value of the area under the receiver operating curve will be given to a model which ranks the objects in this order. And be careful with this metric because the random ranking will be scored as 0.5, like 50%, and the ideal ranking will be scored as 1 or 100%. So if you see the values closer to 0.5, it means that your ranking is completely or close to a random one. The next metric is logarithmic loss. This is a very good metric for probabilistic problem statement because it helps us to figure out how close the predictions are to the actual values. So we score the model higher if all the objects which belongs to a target class has the probability closer to the 1, right? And all the objects which belongs to non-target class have probabilities closer to 0. So it helps us to assess this exactly. Now let's take a look on the process of calculation those metrics. For calculating metrics like precision, recall, and F-score, we need to first calculate confusion matrix. This matrix helps us to see the actual values versus predicted values and figure out what are true positive, false positive, true negative, and false negative values. And based on those values, we can then calculate precision, recall, and F-score for each class and the average ones, of course. When it comes to probabilistic models, you might want to see what is the quality of model on different levels of thresholds, because sometimes you might to come up with your own rule. How do you transform the probabilities to the labels? For example, you might use different thresholds, like for example, give the label target class for all the objects which have probabilities higher than 80% or maybe higher than 50%. It's almost always up to you. So for having the good observability of the quality of predictions, you can go for the precision recall table when you have some step size for your thresholds and calculate metrics like true positive, false positive, precision, recall, F-score for different thresholds so that you can see what is the optimal threshold for you. And of course you can build some visualizations like this, which you can see right now. This is the class separation quality, and such visualizations available in Evidently as well. Together with such visualizations, you can always analyze errors. For classification, that's quite tricky, but you still can do that because we can divide our errors by type, like false negative and false positive, and then you can even explore the dependency between feature values and the types of the errors. For example, you can build distributions for any numerical features or even categorical ones for different type of errors. For example, see how the feature like mean perimeter, for example, like here, distributed for true negative values and how it distributed for true positive values, as well as all the other groups, and see whether there are some shifts in the distributions, which means that, for example, for higher value, we tend to have more errors of one type, and for example, for lower value of such feature, we have more errors of the false positive, for example. So it's pretty handy for coming up with some good insights of what's going on with the model. And together with distributions, you can always analyze categorical values, like you can see in this picture. For example, you can plot the different predictions for different categories and see whether your model tends to have more specific errors for different categories of categorical features. We also have a very nice tutorial which I want to recommend to you, which is an example of comparing two classification models. So if you do have a lot of classification models in production and you need to conduct a lot of experiments, it might be interesting to you. Let's move to the regression quality metrics. In order to calculate regression performance, again, we need to introduce to our model input feature, like we did for classification models. Then we will generate the output, but unlike classification models, regression model generate for us numerical output, which we need to compare then with some numerical fact values in order to estimate the difference. Based on this difference, we can then calculate quality metrics, and there are plenty of such metrics because there are a lot of things which we can make with these numerical errors. So basically we can calculate mean error, mean absolute error, squared error or root mean squared error, mean absolute percentage error, and symmetric mean absolute percentage error. Let's quickly discuss them. Mean error is the very nice metric in terms of interpretation. You can easily grasp the meaning of the mean error because it's just an average of the errors, but in case you have quite a lot of positive and negative errors, where your model underestimate or overestimate the demand, those errors will overcompensate one another. So some positive values will cancel negative values, and you can see that your error is much lower than it actually is. To tackle this effect, we can move from mean error to mean absolute error. And in this case, we will first calculate the absolute value for each error, so all the negative values become positives. And after, we will calculate the average on top of these absolute errors. So this will give us a little bit more information, in some sense, of course. Together with mean absolute error, we can calculate some square errors. This is very nice if you want to penalize your model for larger errors higher. In this case, you could go for squared error, I mean mean squared error, of course, or root mean squared error. Taking the root helps us to move from the initial scale, I mean scale in what we measure the actual target function, so that it's a little easier to interpret the results. Finally, in case we work with the dataset where we have quite a lot of objects with different scale, I mean if we have target equal to like tens and we have target values equal to millions or thousands, in this case the errors from the objects from larger scale will contribute to the mean error more. If you do not want to have this effect, you can move from the actual values to percentage values. So in this case, you will average percentage error, and all different objects, which are objects from different scales, tens and thousands and millions, will contribute more or less the same. And together with mean absolute percentage error, you can also go for symmetric mean absolute percentage error, but be careful here. Firstly, because there are at least two different ways how you can normalize this metric, and secondly is it's called symmetric, but actually it penalizes our model for overestimation and underestimation differently. Sometimes this is exactly what you want, but if not, then better go for the other metric. Now let's quickly discuss the errors, because when you have a regression model, you can easily analyze the residuals of your model. So basically you could start from the plots like predicted versus actual values, because it's quite easy to grasp what patterns your model follow and what do not. For example, from plots like one you can see on the screen now. And together with actual and predicted values, you can build any error over time. For example, mean error, because you will see how much the error of predicted values different from zero, so that you can again derive some patterns or maybe see some dependencies between the time and the error. Maybe you tend to have a bigger errors during weekends, maybe during nights, maybe during the hour of peak demand. Well, such panels helps you to see that easily. When it comes to error analysis, it's quite important to detect where your model tends to underestimate and overestimate the demand. For example, if you work on a problem statement where you need to predict the demand for some services or some products, you might have very clear vision of how much the underestimation and overestimation costs to you, so that you can connect these errors with the business metrics and see how to optimize your model better, to make sure that you really optimize the business process. Well, for example, you can come up with the plots like this, where you have a plot like predicted versus actual values, and by having such plots you can, for example, select the objects where you have biggest underestimation errors, the object where you have bigger overestimation errors, and then I'll analyze them closely. For example, you can try to see what are dependencies between the feature values and the type of the errors in order to figure out how the values of different features influences the errors. Maybe you will have something like what you can see in this plot. This is the plot from the bicycle demand prediction problem statement, so it's very well-known data set where we have strong seasonality. And for example, if we do not really take into account the seasonality and try and model for some short period of time, we can easily see that the model, for example, like this, tends to overestimate the demand when the humidity is higher and underestimate the demand when the humidity is lower. So that's how you can analyze the connection between the features and the type of the error and come up with some good insights, especially if you have a clear vision of what product do, or if you have some access to business analysts and product managers. So altogether, you can come up with good insights and maybe easily solve some issues. Finally, let's take a look at ranking quality metrics. From one point of view, you might see that the ranking problem statement is very similar to the regression one, because in both problem statements, we output the numerical values, which we can then compare to some actual data. But when it comes to regression models, we are mostly interested in the absolute values, so we want to have the precise outputs. But when it comes to ranking model, we are mostly interested into the relative order of the objects. So the idea is to be able to rank or order objects by the predicted rank. This is why we are mostly interested in the relative order. The idea of most ranking models is to let us order the objects, either if we build it for search engine, for example, where we need to find out what are the most relevant answers, the most relevant pages for each query, or if we build the movie or product recommender system and try to find the best objects, the best products or movies for each particular user. We need to know what the ranks are so that we can order and take the top best objects. When it comes to quality metric, we need to estimate the order, so that this is why we cannot really reuse the regression metrics and we go for some specifics. Very wide useful metrics are cumulative gain, discounted cumulative gain, normalized discounted cumulative gain, procedural recall, and lift at k. Let's take a closer look to those metrics. And we will start from the cumulative gain. Cumulative gain helps us to estimate the quality of our recommended objects, and the idea of the cumulative gain is to calculate the cumulative value of the recommended objects, so that it doesn't take into account the exact order of the objects inside of our recommended list. So that if you have two different lists of recommendations with the same objects, but in different order, the cumulative gain would be the same. I believe everyone who worked closely with recommender systems know that all the users are different. And for example, for some users who has a huge history of the interactions with the service, we can recommend quite a lot of relevant products, for example. But for some users, especially for new ones, it's really hard to come up with the good recommendations. This is why if we use discounted cumulative gain, it can be quite hard to compare different algorithms, because it doesn't help us to take into account those specific of users. What we can do here is try to calculate ideal cumulative gain, so it's the quality of the ideal ranking, where for each object, in our example for each user, we build the list of recommendations in the ideal order. And if we then divide discounted cumulative gain of our recommender by the ideal cumulative gain, we get this normalized discounted cumulative gain, so-called NDCG. This is quite good metric because it helps you to normalize the evaluation irrespective of the recommender list length, for example, or irrespectively to the amount of the relevant objects in the list, right? So that's quite important. And well, together with such metrics, there are precision at k, recall at k, and lift at k. This is quite good metrics even if you use the classification model to build your recommender system. Because if you have any model which can give you either probabilities or ranks or whatever value which you can use to the order, if you build your recommender system or other system in a way that you use only top k results, then you can easily calculate precision at k and recall at k. So precision at k will be a share of the relevant objects in the top k results by model, and recall at k will be the coverage of the all relevant objects among top k results. Here is also a lifted k metric, which helps us to compare the quality of our model with the random ranking. The idea is that you divide precision at k from ranking of our model by the precision at k calculated over random ranking. When it comes to ranking models, you can use quite a lot of metrics, so-called beyond accuracy, because if you build a recommender system, that you need to pay attention not only to the relevance, but to the other properties of your system. For example, it can be metrics like serendipity, novelty, or diversity if it makes sense for your system. For example, if you need to make sure that you recommend to user something new, something relevant, something that this user cannot really discover without the help of your system, then together with some precision at k and recall at k, you might want to measure also novelty and diversity. You might be interested in a metric like coverage, popularity based, or any custom metrics which make sense to your problem statement. This is why again and again I tell you that it's very important not to limit yourself with some standard metrics, which depends only on the type of the problem statement, but also try to get a deep understanding of your system, of the business. You try to optimize and come up with some custom metric, like popularity bias. Do you really tend to recommend more popular products than the new one or not? For some system, this is a good thing. For the others, it's not. So it's very important to take the specifics of your product and come up with some good custom metrics. So finally, let us discuss some considerations for production model performance monitoring. It's essential to pick the right metrics. And here are some usual supplies. If you had some rules or heuristics you used during the experiment phase, please reuse it during the monitoring. For example, I bet you never used accuracy for unbalanced classification problem during cross-validation and holdout tests, so do not use it for monitoring as well. Consider using a proxy business metrics. For example, if you are lucky enough to know the cost of each type of errors, for example, for overestimation or underestimation for regression problem, you can easily introduce these costs to your monitoring and calculate not only the mean absolute error, but also the loss, for example, in an economic way, economic loss, right? Not all evaluation metrics are useful for dynamic production monitoring. And even for cross-validation, if you know that you are going to use only part of your predictions, like for example top 10% or top 10 objects, then it makes sense to measure quality exactly on this level so that you do not get fooled by the average values. And same works for monitoring, of course. And finally, consider custom metrics. We discussed it quite heavily. The choice of the right metric is essential, but together with this choice, we need to do a couple of more choices. For example, the choice of the aggregation window size, because it's very important to make sure that you calculate your metrics in the right windows. Depending on the frequency with what you get data and other data properties like seasonality, for example, you might monitor your quality metrics in different windows, like for example each 10 seconds, each minute, each hour, daily, or maybe every 7 days. It can be independent windows, it can be like sliding windows where, for example, you have specific step size, like equal to 1 day, but your window size is equal to 7 days, so every day you recalculate quality metrics, taking into account previous 6 days and the current day as well. So it's all up to you, and you should carefully decide on those parameters. If you're lucky enough to have some historical data, do not hesitate to calculate the quality metrics on top of your historical data and check whether the parameters you choose to calculate your quality metrics really helps you to detect some issues, especially known one, which you knew happened before, so that you can see whether your metric alerted on the known issues on top of historical data or not. Together with aggregation window, consider split your data into different segments, for example by countries, other regions, by operation systems, by device type. Again, depending on the system you try to optimize, and make sure that you do not lose the quality on the smaller segments. Well, basically that's it. We discussed quite a lot of things about calculating quality metrics for classification, regression, and ranking models, and our next part is likely practice. We are going to build a quality report and see how we can do it with help of Python and Evidently.